Hello everyone, welcome to Sai Tutorials Jamkandi. In our tutorials, 10th class Kannada medium, English medium, and maths, science, English classes are available, and also PCMB classes are also available in the regular classes as well as in the online classes. So please join us and learn the things. So, dear students, in today's session, let us discuss the further syllabus, further concepts related to your syllabus. uh, Physics chapters for second PUC. That is, we are at the third chapter, current electricity. We all have discussed uh, concepts related to your syllabus. Now, uh, already Ohm's law is over, resistivity or specific resistance is over, and some of the properties or some of the factors related to the resistivity or specific resistance is over. So, in this today's session, let us study about conductivity. See, I have told you in the previous session about introduction to the conductance and conductivity. See, conductance. Conductance means if I consider any kind of material, any kind of so if I consider any kind of material, if I consider any kind of material which have the capacity to pass the electrons, which have the capacity to flow of electrons, so such a property are called as conductivity or conductance. Okay, so you can also say that it is a conductivity. Okay, it is also conductivity is denoted by the letter that is sigma. Is it or not? Sigma. It is the reciprocal of resistivity. Okay, it is the reciprocal of resistivity. See, the SI unit of sigma is per Simon, Simon per meter. See, resistivity, it is Simon. See, SI unit of sigma is, I have told you that SI unit of resistivity is ohm meter. Okay, ohm meter. But the SI unit of resistivity is per ohm per meter. So, per ohm can also be said as Simon. Okay. See, the reciprocal of the resistivity is called as a conductivity. So, SI unit of sigma, conductivity is resistance. Simon per meter. The dimensional formula of sigma is I square m to the power of minus 1, L to the power of minus 3, and T to the power of 3. This is the expression for conductivity as well as the SI unit. Okay. Next we come to the conductance. Okay. See, conductance is nothing but the reciprocal of resistance. Okay, I have told you, I have discussed what is resistance and what is resistivity or specific resistance. See, the reciprocal of resistance, it is called as a conductance. It is denoted by the letter that is G. So it is equal to the 1 divided by reciprocal of, 1 divided by R is nothing but reciprocal of the resistance. So that is also equal to the resistance is given by rho into L divided by A. So 1 divided by R is nothing but R is equal to resistance. R is equal to rho into L divided by A. So in case if you keep 1 by R as a reciprocal, it will become A divided by rho into L. Am I right or not? Okay. Now 1 by rho is equal to the sigma. Is it or not? We have discussed in here resistivity. Conductivity. The reciprocal of resistivity is nothing but conductivity. That's why I have written G is equal to sigma into A divided by L. The SI unit of G is Simon. Okay. Simon is the cells per ohm. Okay. These are SI unit of uh, you can also write a Simon like this. Okay. The reciprocal of resistance is given by G is equal to 1 by R. Okay. So G is equal to A divided by rho into L. So where 1 by rho is equal to the sigma into A divided by L. The SI unit of G is Simon. So Simon is written by, Simon is written by like this. Okay. Now the dimensional formula of conductance is I square m to the power of minus 1, L to the power of minus 2, T to the power of 3. This is the conductance definition and its mathematical expressions and SI unit and also dimensional formula. So now let us derive relation between J, current density. I have told you in the first class of this chapter, J is denoted by the letter current density, sigma is the conductance and conductivity and E is the electric field. Okay, so these are related by the formula J is equal to sigma into E. In the vector form, we have to denote J bar and E bar in the vector form. So let us derive this expression. Yeah. Relation between J, that is current density, and E, electric field, and also sigma, that is conductivity. Okay. Now here J is the current density. J is the current density and sigma is the conductivity. And E is the electric field. Okay, so now let us derive the expression for these three equations. I mean, equivalence form of Ohm's law. We can also write it as equivalence form of Ohm's law. Okay, equivalence form of Ohm's law. So let us derive the expression. So we know that current I is equal to, in terms of drift velocity, that is NEA into VD. Is it or not? We know the current, that is I is equal to, in terms of drift velocity, number of electrons and the electrons, and also area, surface area of that conductor, and also the drift velocity of the uh, ions present in them. So now, but we can also write this VD as E, capital E, into tau divided by M. Is it or not? Is it or not? So substitute these two, to equation number 2 in equation number 1. Okay. Substitute equation number 2 in equation number 1. Now this will become I is equal to NE A. So what is VD? E E tau divided by M. Or you can also write it as I divided. If you take A as A to the LHS side, it will goes to the denominator side. The remaining is N E square into E into tau divided by M. Okay, is it or not? Now, please note this. Okay, that is equation we have got here, that is I by A is equal to N E square E into tau divided by M. Let us consider this as equation number 3, where I by A, okay, I by A, current divided by, current per unit area is equal to the current density. Is it or not? And M divided by N E square into tau is equal to resistivity. Is it or not? Okay, we know that current per unit area is the current density, and M divided by N E square into tau is equal to the resistivity. So if you substitute here, J is the current density. And rho is the resistivity. Is it or not? And rho is the resistivity of the substance. So if you substitute these two equation in equation number 3, we will get J is equal to 1 by rho into E. But we know that 1 by rho is reciprocal of resistivity, that is conductivity. So the J will become sigma into E. This is the relation between the current density J and conductivity, and also the electric field. This is also equal to the equivalent form of Ohm's law. So let me repeat. Relation between current density J, conductivity is sigma, and E is the electric field. So it is also called as equivalent form of Ohm's law. So if you derive the current, what is the formula for current in terms of drift velocity? That is NEA into VD. But VD is equal to the formula, that is E capital E into tau divided by M. So if you substitute equation number 2 in equation number 1, you will get I by A is equal to N E square into E tau divided by M. Okay. So where I by A is the current density, that is J, and we know that m divided by n e square into tau is equal to resistivity. So if we substitute this equation in equation number 3, we will get J is equal to 1 by rho into E. But 1 by rho is equal to conductivity. I mean reciprocal of the resistivity is reciprocal of the resistivity is equal to the conductivity. So J will become is equal to the sigma into E. I hope this concept is clear. So this is what the formula we have got here. So it is in the vector form, that is J bar is equal to sigma into E bar. So there are some limitations of Ohm's law. Let us discuss one by one. Limitations of Ohm's law. So what are those limitations? Let us discuss. Okay. Let me change the pen. First one. See, Ohm's law is first and foremost limitation. That is limitations of Ohm's law. Ohm's law is applicable only to metallic conductors. Okay, only to metallic conductors at moderate temperature and moderate potential differences. So Ohm's law is only applicable to the metallic conductors at that too at moderate temperature and moderate potential differences. This is a kind of limitations related to Ohm's law. So if you consider the metallic conductor, I mean Ohm's law, it is only applicable for metals, okay, metallic conductors, not applicable to any other materials, okay. It is only applicable to metallic conductors, that too moderate temperature, okay, that too moderate temperature and moderate potential difference should be applied to that material. So this is one kind of limitations. Okay, second one is Ohm's law cannot be applied to conductors maintained at high temperatures or very low temperatures. Okay, this cannot be applied to conductors maintained at very high temperatures or very low temperatures. This this temperature should be in between, lies between very high temperature and low temperature, I mean moderate temperature. Only at a moderate temperature should be applied to that kind of materials. Okay, this cannot be applied for a conductors maintained at a high temperatures or very low temperatures. Okay, or you can't apply it to the any kind of semiconductors or semiconducting devices, because this is applicable only to the metallic conductors, which is having the metallic conductors, I mean low resistivity power, the materials which have the low resistive power, that are metallic conductors. So if you apply the I mean if you apply it to the semiconductors or semiconducting devices, Ohm's law will not be applied. Okay, next is to conductors across which very high potential difference or very low potential difference is applied. Okay. In case of, if you consider in case of potential differences, the conductors, you can't be applied to the conductors across which high potential difference or very low potential difference, but this potential difference should be moderate. This potential difference should be moderate. Okay, these are some limitations of Ohm's law. Okay, first one is Ohm's law is applicable only to the metallic conductors, that too at moderate temperature and that too at moderate potential difference. This is what they have said here. Okay, but Ohm's law cannot be applied to conductors maintained at high temperatures. So whatever the temperatures given to the material, that is conductors maintained, this Ohm's law cannot be applied to such materials having very high temperatures, also for very low temperatures. They should not be applied. And also for the, it should not be applied to the semiconductors or semiconducting devices. Okay, the last one is this Ohm's law cannot be applied to conductors across very high potential difference or very low potential difference. But this potential difference should be moderate, lies between the very high potential difference and very low potential differences. So this is what the limitations of Ohm's law. Okay. So in case of VI characteristics of Ohm's law, there are some variations between the potential difference and voltage and current. I have told you in the what is Ohm's law, and there are some variations of current, that is I current in the conductor, and also the uh, uh, to that corresponding current or to that corresponding voltage, how much variation is there in between the conductor, current, and also the voltage. Okay, the variation of current with a voltage V at various temperatures for any device is called VI characteristics. So let us discuss one by one. So for an ohmic device, VI characteristics is linear. Okay, they have shown here. This is the VI characteristics of ohmic device, that is metal conductor. Ohmic devices are metal conductors. See, suppose if you consider the metallic conductors, the VI characteristics is linear. This is what the linear. Okay, it is linear for a ohmic devices. For a non-ohmic devices, the VI characteristic curve is non-linear. Okay, these are non-linear. These are non-linear. Curve is non-linear. So if you consider the non-ohmic devices, suppose if you consider the non-ohmic devices, the characteristics of, VI characteristics always non-linear. That is non-linear. This is the non-linear. Okay. So this is the VI characteristics of ohmic and non-ohmic devices. So here the next concept, that is effect of temperature on resistance. Okay. So how it will show effect of temperature on resistance, how it will affect on resistance, the temperature, how it will affect on resistance, let us study. Okay, then see, if you consider any metallic conductor. Okay, if you consider, let us consider any metallic conductor like this. This is the metallic conductor. Okay, so it is due to if you apply resistance. Okay, so if there is any metallic conductor, there will be a large number of electrons and ions present in the this conductor. Okay, so if you apply some kind of temperature to this, if you pass the current to that metallic conductor, there will be some kind of collision between the drifting electrons and the ions present in the metallic conductor. I have said. Okay, so if you apply metallic conductor current, that is due to the collision between the drifting electrons and the ions present in the metallic conductor. Electrons and ions. Okay, so when the temperature of the conductor increases, the vibration in the ions of the lattice increases. Is it or not? So if I increase the temperature of the metallic conductor, so if I increase the temperature of the metallic conductor, the vibration or the collision between the ions and the electrons will take place, also increases. So the collision between the electrons and the ions become more frequent. Okay. Now, therefore, the opposition to the flow of electrons increases. Okay, the opposition to the flow of electrons will increases. That opposition is called as resistance. Okay, that opposition is called as resistance. Okay, so resistance of the metallic conductor increases or decreases with the increase or decrease of the temperature respectively. Okay, see, the effect of temperature on resistance will depends. How it will depends? It depends on the increase or decrease in the temperature. Okay, the resistance of the metallic conductor increases or decreases. When it will increases or decreases? When you increase the temperature, or when you increase the temperature, the resistance also increases, or when you decrease the temperature, the resistance also decreases, like that. So let's suppose consider, uh, let me derive here. Suppose R naught is the resistance of the conductor at 0 degree Celsius, and suppose let us consider R naught. R naught is the resistance of the conductor at 0 degree Celsius. Okay, and R is the, I mean, R is equal to the resistance of the conductor at T degree Celsius. Okay, so increases or decreases depends upon like this. Okay, R minus R naught. Okay, increase in the resistance, that is R and R minus R naught. So that is equal to the, that is directly proportional to the R naught. And in first case, and suppose if you consider a T temperature, R minus R naught is directly proportional to T, is it or not? Okay. Now this T is also equal to the del T. So that's why I have written R minus R naught is directly proportional to R naught into delta T. This is equation number 1. So if you want to remove the proportionality constant, that is, so if you want to remove the proportionality constant, that is R minus R naught is equal to alpha. Okay, alpha proportionality constant alpha, that is T. This is equation number 2. Okay, where alpha is the temperature coefficient of the resistance. So resistance of the conductor at absolute temperature T is given by RT is equal to R naught into 1 plus alpha into T minus T naught. Okay, where rho is the resistivity of the material depends on its temperature. For a small variation of temperature, that is rho is equal to rho naught into 1 plus alpha into T minus T naught. So where alpha is the temperature coefficient of the resistance. So the resistance of the conductor at absolute temperature is given by RT. That is, at absolute temperature T, RT is equal to R naught into 1 plus alpha into T minus T naught. So alpha is equal to RT minus R naught divided by R naught into T minus T naught. So it is also equal to 1 by R naught. So RT minus R naught is del R and T minus T naught is delta T. So the SI unit of alpha, I mean temperature coefficient of resistance of the material, is given by per Kelvin. So R versus T graph, that is y-intercept, that is R naught, and slope is equal to R naught into alpha. So alpha is equal to slope divided by y-intercept. This is all about the effect of temperature on resistance. So there is some kind of notes to be remember, that is alloys. See, alloys generally have low temperature coefficient of resistance, that is alpha is low in case of alloys. So in other words, the resistance values do not vary appreciably with the change of temperature. Why? Because the temperature is low here, that's why the resistance values do not vary appreciably with the change of temperature. So it is for this reason that manganese and constant coils are used in resistance boxes. Which kind of materials are used in case of resistance boxes? That is magnet and constant coils are used in resistance boxes. So semiconductors have negative temperature coefficient of resistance. Okay, see, in case of semiconductors, those are non-ohmic devices, is it or not? So they have a negative temperature coefficient of resistance, while metals have positive temperature coefficient of resistance. Okay, semiconductors have negative temperature coefficient of resistance, while metals have positive temperature coefficient of resistance. So, dear students, in this today's session, we have learnt about what are conductors, what is conductance and conductivity. So, relation between the current density, so conductivity, and also electric field. Also, Ohm's law in vector form. There are some kind of limitations of Ohm's law we have learnt in this session, and also the VI characteristics. Okay, the VI characteristics, how it will vary in case of ohmic devices and also non-ohmic devices, and also the effect of temperature on resistance. It always depends on the temperature. Resistance will always depends on the temperature. How you will give the temperature, the resistance also vary in such a manner. So this is all about the effect of temperature on resistance. Okay, this is all about the concepts related to your syllabus in this today's session. So in the next session, let us discuss the further information or further concept related to your syllabus. So let us wind this session at this point. So dear students, please note down whatever I have said you in this session, and learn the things as easy as possible, and make it easy and clear the concept. Then only you will understand the things very quickly. Okay, and you will not forget it. So by saying this, I am going to wind up this session today itself. So thank you guys.